This video is to demonstrate some of the forces between the magnets. There's been several requests about measuring these forces instead of just saying, well, this is stronger than that. So that's what I'm going to try to do for this with this video. This setup is not exactly the same as anything that Floor has posted. Using some of the ideas from Floor and doing some studying, I came to the same conclusion he did. You can't really shield one magnet from another. You can put mu metal between them, but then both magnets are just attracted to the mu metal, so it doesn't really accomplish anything. But you can balance the forces, which he's been demonstrating in several of his videos. And I've come up with a slightly different way of balancing the forces. This stack of magnets is south on the top and north on the very bottom. This south of magnets is south on the top and north on the very bottom. These two magnets are south on that side and north on this side, which means that they're slightly repelled from this, but you can see not much. There's a very slight bit of kickback there, but once you come all the way in, it's balanced. So the question is, does this force here a lot less than this force? So I've gotten a fish scale that measures in pounds and ounces and also measures in kilograms. So we're going to turn it on. I'm going to turn on the backlight. If I can figure out how to again. Come on. There we go. We're in pounds and ounces, and the backlight is on, so to make it a little bit easier. I'll do this a couple of times, but we want to measure. This thing has a bad habit of wanting to set itself to zero or record if it's longer than 2 seconds in the same position. So we got it zeroed. We're going to pull in, and you're going to see the force goes up to a pound. And I've done this over and over again. It actually averages out about 1 pound and 5 ounces. Okay, that's with no magnet in between. When I get to the same distance as here is what it would be with it in there. 1 pound, 5 ounces. Put this in there. And I think it went into record. Let's try that again. About 4 ounces. Three ounces. If I've done this several times, and it averages out about 3 ounces to 4 ounces before it gets where it's actually attracted to this magnet. You can see that it's 1 pound and about 4, 5, 6 ounces to pull it in when this magnet is not there. Now, this magnet is actually touching, those two are actually touching. If I had a stop where this was off slightly, this would reduce this pressure even more. And I hope you can see that this, zero it again, but it takes very little force to pull that, 7 ounces or so. And that's because it's dragging. When I move that back slightly, it's even less. And we'll hold it off just barely with my fingers. 5 ounces. And I was holding this off just slightly with my fingers, which you probably couldn't see in the camera. Whoops, it went in record again. 5 ounces or so. So it doesn't take but a few ounces to move that. It doesn't take but a few ounces to move this. Let me see if I can switch this to kilograms, and we'll do it over one more time. Okay, we're in kilograms. I haven't done this in kilograms, but we're going to do it now. I'm zeroed. Get hooked up here. Let's try it again. Oh, I didn't actually okay it. Come on. .5, 0.6, somewhere right in there, a kilogram. I'll do it again. Whoops, record it again. At 0.5, 0.6, without the control magnet there. .14. I don't know if you can see that. I'm trying to keep it where you can see it. 0.14 again. .14. I think that gives you an idea. There is quite a bit of difference. Oh, we didn't measure. Let's measure like that. Well, I think we did, didn't we? See, that's 0.5, 0.6, 0.68 actually. It looks like it got as close as I can get it there. That should give you an idea of the different forces involved. This force without that is quite a bit stronger, and it takes very little to move that if this is not actually rubbing. Almost nothing to move it. So there you are.